Transfer coefficient and its significance. In previous lecture we have seen that the energy barrier for oxidation at applied potential is less than the energy barrier that is observed at equilibrium condition by a fraction of the total energy change. So here this fraction was actually 1 minus alpha into the energy term. So here alpha is actually the transfer coefficient and its value depend on this cross section, that is the shifting of this energy barrier through this one with application of applied potential, which can be either positive or negative, as in this case the applied potential is positive. The cathodic barrier towards the lower energy. Now let's redraw the geometry of this intersection region. Here the transfer coefficient alpha is the measure of the symmetry of this energy barrier, and we have drawn the amplified region of the free energy plot that have shown the effect of the applied potential, which have moved the energy barrier to lower energy. So here we have the part of energy barrier that is for equilibrium potential, and this one is for the applied potential. And it is assumed that those curves are actually linear in this region. So the angles can be drawn as theta and phi. So this angle and this one are equal. And let's suppose the length of this intersection is x. So according to this figure, the angles can be defined by the equation 1 and 2. So this one is showing the value for the theta and that one is for phi. In both cases, this length is acting as base, whereas the fractions of energy, that is alpha NFE and the 1 minus alpha NFE, are considered as perpendicular for these two triangles containing two angles. Both equations have a common term, that is x, so we can compare these two equations as shown here. So these factors are common, so we get alpha 10 of phi that is equal to 1 minus alpha 10 of theta, and this equation can be rearranged as and finally we can calculate the value of alpha using equation given here. So we have the final expression using equation number 3. So from this expression we can calculate the value of alpha for any free energy curve using the intersection of free energy curves with application of the potentials, whereas we need to measure only two angles for the calculation of this alpha. Now consider a few points in which the first one is if this intersection is symmetrical, then the angle theta and phi are equal. When these are equal for the case 1 in which the intersection is symmetrical. So for this case, the value of alpha calculated using equation 3 will be equal to half. For this case, that is the case number 2, in which the angle theta, as in this diagram, theta is greater than the phi. So for this case, if we calculate the value of alpha from equation 3, the values of alpha will be higher than the half or 0.5, and maximum it can be equal to 1. So the range of values we can get for the higher angle, that is theta. So these values range in half to 1. For the third case, we have the value of alpha that must be less than half, that is because of the theta is smaller than phi. So the value of this case will lie between half and 0. But experimentally, the value of alpha usually measured in the range of 0.3 to 0.7, and it is approximated to be half in the absence of any measurement, that is the potential variation of the electrode. Now from this figure we can see that the relationship of the transfer coefficient to the angles of intersection of the free energy curves. So here these two angles theta and phi are equal, and the value of alpha is equal to half, and this one is the ideal case when usually observed in the absence of actual measurement. As it is mentioned earlier that the value of alpha ranges between 0.3 to 0.7 experimentally. So these are the real cases. So in this case we can see that this angle theta is smaller than the angle phi from this area of intersection, and the value of alpha is less than half. As for this case, the phi is smaller than the theta, and the value of alpha is higher than half, and with the maximum value of 1. So here we can see that the variation of the value of alpha, that is the transfer coefficient, is an indicator of the symmetry of the barrier to reaction. From this figure we have seen that the angles theta and phi would depend on the location of the this perpendicular, this one intersection, which turn the value of alpha either half or the less than half or higher than half. So we can see that the value of these angles or the intersection is depending on the type of potentials applied. So consequently, the value of alpha is actually dependent on the potential. In next lectures, we will discuss about the kinetic models that are based on the electrochemical potentials.